This is the 2012 free response, and we're going to look at questions 1, 2, and 3. In the year 2012, questions 1, 2, and 3 were with a calculator. So all three of these questions, you may use a calculator. So let's take a look at question number 1. The temperature of water in a tub at time t is modeled by a strictly increasing, twice differentiable, important, I want to underline that or circle that, twice differentiable. So there is a first and a second derivative. If you're wondering, what does twice differentiable mean? A first and a second derivative. So let's go back again. The temperature of the water is modeled by a strictly increasing, so that's important to note that the temperatures always increase, and the function's name is W, where W of t is measured in degrees Fahrenheit and t is measured in minutes, and I can see that in the table up here. At time t equal to 0, the temperature of the water is 55 degrees, so that is the temperature of the water when we begin. Values of W of t, which is the temperature of the water, at selected times for the first 20 minutes are given in the table above. Use the data for letter A, use the data in the table to estimate W prime of t. Show the computations that lead to your answer, use correct units, interpret the meaning of your answer in the context of the problem. So first of all, notice that they're asking us to do giving us several directions here. First of all, we're using the data in the table. We have to pay attention to that. The first thing they want us to do is to show our computations for approximating W prime of t. And then the second thing that they want us to do after we do that approximation is to interpret the meaning of that derivative. So there are two things that have to be accomplished here. We know that from class when we estimate a derivative from a table of values. So we're trying to estimate the derivative at 12, but notice the number 12 is not in the table. However, 12 is somewhere in between 9 and 15. So we know when we're estimating a derivative, we're going to go one data value above and one data value below, and we're simply going to do change in y over change in x, which is simple basic slope. But you must show the difference quotient to get your point. So when we come down here and look at the work, you can see for letter A, let's just start with the setup. So the first thing we have to show is change in y over change in x, and you do not have to do it symbolically as they did here at all. You can go straight to the numbers, which are right here, but there needs to be a difference quotient, and this difference quotient does not need to be simplified. I want to keep reminding you of that just because you're allowed to use a calculator does not mean you have to simplify, and that will give you the 1 point for your estimate. Now the interpretation, in our class we have a standard sentence that we use, so this might not be the standard sentence. So I'm going to read to you exactly what we would say. Since we're interpreting a derivative always modifies its preceding function. So in this case, W prime is going to modify W. Remember, W is the temperature of the water. So we would say, and you can check your answer based on what I'm telling you, at 12 minutes, I believe it is, let me make sure. Yes, at 12 minutes, the temperature of the water is increasing at a rate of 1.017 degrees Fahrenheit. Or you could quote this difference quotient right here. You could just put that right in there. Degrees Fahrenheit per minute, because W prime of 12 is greater than 0. So that would be your interpretation. And what I mean right here when I say no bald answers is you cannot just report 1.017 or 1.016 and expect to get credit. You will not get credit for that bald answer. All right, let's go back and look at letter B. In letter B, use the data in the table, so everything is referring us back to the table, to evaluate a definite integral. So notice that we're integrating W prime. So when you integrate a rate, you lose the rate. So if we integrate W prime, we simply return back to W. And we're going to use FTC part 1, so we would have W. I'm going to type this. There's no way I'm going to try to write that. So W of 20, because remember, we go back to W, minus W of 0, and that is the upper bound minus lower bound. That is the FTC part 1. And then again, notice that they're asking us or telling us to interpret the meaning of this integral. So let's start with letter B. First thing we're going to do is we're going to report out the W of 20 minus W of 0, which is 71 minus 55, which is 16. So we're going to get 1 point for reporting the correct value. The interpretation is, the sentence that we would use in our class is, the definite integral represents the change in the amount, the change in the temperature of the water from 0 to 20 minutes measured in degrees Fahrenheit. Now, you don't have to necessarily report that 16 again. You've already reported it out, so you could say what I said. Notice when I stated my answer, I did not state had warmed 16 degrees. So again, I said the definite integral represents the change in the temperature from 0 to 20 minutes measured in degrees Fahrenheit. That sentence would be perfectly fine. All right, letter C. In letter C, we are finding the average temperature. Again, in my class, ladies and gentlemen, we know to insert words average value of the temperature of water. So we want the average value of temperature, and remember that temperature is W. We want the average value of W, not W prime. Words are so very important. So they're telling us that the average value is this integral, and you can see that they agree with me, hopefully so, since I want to be correct, that we are finding the average value of the temperature. Use a left Riemann sum with 4 subintervals indicated by the data. Now what that means is the intervals might be equal or unequal. It's your job to figure out whether those equal or unequal. Then the second thing, does this approximation over or underestimate? Now you've seen this in a couple of free responses already. So that's going to have to do with that part of the prompt that we read earlier that told us that W is a strictly increasing function. The data is strictly increasing. Okay. So let's begin by talking about our left Riemann sum. So let me erase some of this off of here and get it out of the way. So for a left Riemann sum with 4 subintervals, we're going to have one rectangle here. That one is a width of 4, a width of 5, a width of 6, a width of 5, and then left endpoint number 1, left endpoint number 2, left endpoint number 3, left endpoint number 4, and then we don't consider the last endpoint because that would be a right endpoint. All right, so when you go down and you check your work, what we're looking for, I don't really care so much about this line right here, the W of, but there's the 1/20th, they already gave us that, and then I told you the widths and the heights. You can leave your answer in this format right here for full credit. So that would give you the left sum, that would give you the approximation point, and then we're going to report out that we have an underestimate because W is strictly increasing. Now remember, the way I told you to do that is to draw a function that is increasing. So you could draw something like this, and then draw a left endpoint approximation, or a left, sorry, not an approximation, draw a few left endpoints. So I would start at the left and I would go to the right, then I would start at the left and I would go to the right, and then I would start at the left, sorry, this is not great, and go to the right, and you can see that I'm getting an under approximation. So you don't have to memorize it, you just look at it and you'll be able to figure it out. In letter D, for 20 to 25, which is not in the table, notice, the function W that models the water's temperature is given has first derivative. So now we're going from a table to a function. This is the first derivative of a function W from 20 to 25 that also produces the temperature. W produces the temperature. Based on the model, what is the temperature of the water at T equal to 25? Okay, so if you will recall, let's see, where did we do that? Use the data to interpret. Okay, so back in part B, we already found the change in the temperature from 0 to 20. The other thing that we have to realize is that the temperature at time 0, here's that initial condition, the temperature is 55 degrees. So the temperature at 25 minutes is going to be relative to the temperature that we started with. So we're going to start. Now, notice down here you see a 71. But what they're doing there is they're taking the 16 degrees from part B, which is the change in the temperature, okay? And they're adding it to the 55 to get the temperature at 20 minutes. So 55 and 16 gives you 71. So that's where the 71 is coming from. You just as easily could have had in your work 55 plus, and then you could have had the 16 degrees, or you could have you could write the integral from 0 to 20 of W prime plus, and then go to the integral that they have written right here. And remember, this is coming off your calculator, so you're going to evaluate that integral with your calculator. So you get 1 point for the integral, and the integral that they're talking about is this integral right here. That's 1 point if you wrote that integral, and then 1 point for the correct final answer. Okay, in the year 2020, we are not going to be tested on area and volume, but I'm going to go through this problem so that it's there for future students. So if you are looking at this in the year 2020, you may go ahead and move the video forward to question number 2. Number 3. In question number 2, we have, you can see quickly, this is going to be an area volume problem. Let R be the region in the first quadrant bounded by the x-axis and the graphs of ln of x. So over here, and you can see this on your calculator. Remember, this is still a calculator question. Ln of x is the first curve, and over here we have 5 minus x is the curve over here. Find the area of region R. Now, there are 2 ways to do this. There is definitely over here a right side and a clear left side. However, you can do this problem in terms of x or y. You will see that in the work below. But don't go in terms of x and y unless you absolutely have to. Notice that we can simply use 2 integrals in terms of x. If we find this point of intersection right here, and let's see how well this line comes down. That's pretty good. All right, so if we find that value of x right there using the calculator, then we can find the area of region number 1 under ln of x, and then find the area of region number 2 under 5 minus x and add that together. But again, you can do it in terms of y. I just think it's got a lot more places where you can make a mistake. So in terms of, well, they're going to do both. So first of all, we're going to need that that x value for the point of intersection, which is 3.6934, which gets stored into your calculator. And remember, if you're going to do this in terms of y, then you would have to take one of those 2 functions. So let me just show this. So on y equal to clear clear, and we had ln of x. Whoops. Oops, I'm typing on the calculator. I mean on the keyboard, sorry. That would be a problem. Okay, so ln of x is the first function, and the second function is 5 minus x, and you can see that my calculator will produce the same graph, and I can zoom box that, so I'm going to do a zoom number 1, and I'm going to start at the origin. I'm going to press enter because I'm going to start my box there, and I'm going to move the box up this way, over this way. Come on, you can do it. Okay, and then enter. And I get something that looks like what I have on my screen. And so then when I do the intersection of the two curves, 5, second calc or second trace 5, enter, enter, enter. There's that point of intersection, and I'm going to store that. So second, quit, store, alpha A, enter. If I decide to do this problem in terms of y, I'm going to need that long y value, so I'm going to substitute this stored value of x into either of the functions. It doesn't matter which one. Now, since 5 minus x is really easy, I'm not going to use my vars and y bars and all that stuff. I'm just going to do 5 minus alpha a, and that'll give me the y value, and I can store that, store alpha b, and there's the y value stored with the long decimal number if I decide to do the problem in terms of y, which I don't want to, but I might have to do another part of the problem in terms of y. So the number's there if I need it. So if you're going to do the problem in terms of y, you have to change your functions into being in terms of y, so you would have the right curve, which becomes 5 minus y, minus the left curve, which becomes e to the y, if you do this in terms of y, from 0 to this stored decimal number. And we would not write that b, we would write 1.307. And then let the calculator do its work, and there's 1 point for the integrand, that means having correct right minus left, 1 point for the bounds, and 1 point for the answer. And then doing the problem in terms of y, which is what I suggested. Again, we're not going to write the a, we're going to write that value of 3.693 here, but we'll use the stored value on our calculator when the calculator does its job to get 2.986 or 2.985. In letter B, region R, so now let me erase my work because I made 2 regions, but we are only looking at big region R. So region R is the base of a solid for each cross-section perpendicular to the x-axis. So we're in terms of x is a square. Write but do not evaluate. Do not evaluate an expression involving one or more integrals that gives us the volume of the solid. So we know that when we're finding that, we start with, when we're doing cross-sections or making cake, we start with area of a square. So the area of a square, let's do a different color besides yellow. All right, so area is equal to a side squared. So that's our geometry formula for the area of a square. All right, and then we need to know the length of a side. Okay, let me get out of there. Out of the exponent mode. All right, so a side of the square, remember you're going to put a representative slice perpendicular to the x-axis, so it doesn't matter where it goes. However, we're going to have to be really careful because when we go across perpendicular to the x-axis, and here's one representative slice, this is the top, and down here is the bottom. So we know it's top minus bottom. But then when you keep accumulating the area, over here, we change curves. So we have another top minus another bottom. So we're going to need two integrals, and we're going to need that point of intersection. So when we write the integral that accumulates, and so the side, I'm sorry, so the side will be, when I come back here, the side will be, for the first region, ln of x x minus, well, minus nothing, minus 0 technically. And then over here, for region number 2, s is equal to 5 minus x minus 0, because the bottom is 0. So we really don't have to worry about that. Okay, so when we come down here and look at the work for part B, we're going to go from 1 to the point of intersection in terms of x, side squared, so it's ln of x squared, side squared, dx, plus, start at that point of intersection, go to 5 minus x quantity squared, the side squared. All right, so 2 points for the integrands. The integrands have to be correct with the squares. And the order doesn't matter because we're adding them together, so which would not matter which integral you have first as long as you have the correct bounds, and then 1 point for the total expression for the volume. And finally, part C. This is the part where a lot of kids tend to give up a little bit, but I don't want you to give up. It's not nearly as hard as you think it is. The horizontal line y equal to k divides region R into two regions of equal area. So up here I have a horizontal line y equal to k. Now it goes somewhere inside to split the area into two equal parts. So I'm just gonna randomly put it. Let me get rid of some of this other stuff. Well, I might need those words, so I'll leave that. Leave that. Just trying to clean up a little bit here. Okay. So this is the line y equal to k, and I have two regions of equal area. So I'm going to call this region number 1. And down here, I'm going to call this region number 2. So basically, the big idea here is that this line is placed in such a way such that region 1 is equal to region 2. All right, so that's what's happening with that horizontal line. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. All right, so I don't know where y equal to k goes, but I'm going to treat k, what color am I on? I need to change colors. I need to treat k as a number. That's a very important thing. All right, so there are a couple of ways to handle this. If you think about our work from earlier, we already found the entire region of area. So I'll show you a couple of ways that we do down here. So now we're going to have to go in terms of y, because we are accumulating, we're accumulating up to a y value. So they're accumulating the area from 0 to k, that's the y value, so we're sweeping upwards, and we're going to do the right curve minus the left curve, which is what was done earlier in terms of y, and that's going to equal to half of the answer that we produced earlier. All right, so that's one way to do the work, is to take the answer from above, say I'm going to take half of that, and the area from 0 to k, the area of one of those regions is half of the area that I found in part A. Now, some other ways to do that. So notice that the problem asks for an equation, not an expression. And we drew the horizontal line, and we know that we're in terms of y, and there are several variations of the equation that could be correct. So the student could, I'm down here, go from 0 to k, right minus the right side minus the left side, and say that that would be the lower region. That would be what I called region number 2 up above. And we could say that that area is equal to the area from k to 1.307. That was that point of intersection y value of right minus left. So we're literally saying region 1 is equal to region number 2. Or we could take those two regions together and say region number 2, which is right here, I called it up there, and plus region number 1 is equal to my answer in part A, which is the total area. Or I could double one region of area, this is region number 2, and say that's equal to my answer in part A. Sounds way more complicated than it actually is. All right, finally, question number 3. Question number 3 is our geometry question. Let f be the continuous function defined on -4 to 3, whose graph consisting of 3 line segments and a semicircle centered at the origin. So the 3 line segments are 1, 2, 3, and a semicircle centered at the origin. Let g be the function g of x equal to 1 to x of f of t. So in other words, I can see already that by the FTC part 2 that g prime of x is equal to f of x. I assure you it's going to be pretty important that that be written, shown somewhere in your work to get some points. All right, let's start with letter A, which is very direct. Letter A says, find g of 2. Well, that's really easy. All I'm going to do is substitute 2 here, and I'm going to find the area from 1 to 2 of f of t. All right, so if I want to find the area from 1 to 2, here is 1, here is 2 right here. All right, now I'm going to find the area of that region, but to find the area of that region, I'm going to need to know what this y value is right here on this line. So in order to do that, I'm going to write the equation of the line, and you can see on my work down here, I'll try to keep the picture in there. To find the y value at f equal to, write the equation of the line. So y minus 0 is equal to, I can do the slope of this line by rise over run. So I know the slope is -1/2, and I know I have the point 1, 0. So I can substitute the 0 and the 1 and get the equation of the line, and then I can substitute 2 into the equation of the line and get the y value of -1/2. So now I know that this y value is a distance of -1/2, and I'm going to find the area of that triangle by 1/2 base times height. So the base is 1, the height is 1/2, take half of that, and because the area is below the x-axis and I'm moving from left to right, I'm going to get a value, a net accumulation of area of -1/4. All right, then we're going to go to g of -2. So g of -2, I'm going to substitute -2 in place of x, meaning I'm going to go from 1 to -2. So remember, I'm going in the opposite direction. I'm going from right to left. So whatever areas I find, I'm going to have to reverse their signs. So we're starting again. Let me erase some of this. I'm starting at 1, and I'm stopping at -1 at -2, which is here. So I've got to do my geometry. So I'm going to begin by finding the area of this semicircle right here. The area of a circle is pi r squared. The radius of this circle is 1. So since it's a semicircle, it's pi r squared over 2. So that would give me a total area of pi over 2. And since it's symmetrical, each region would have an area of pi over 4. I don't know if I need to break them up or not, but I went ahead and did that. All right, so from 1 to -1, I have positive pi over 2, because remember the area is below the x-axis, but I'm moving in the opposite direction. And then I'm going to subtract the area of the triangle, which is normally positive 3/2, but I'm going to subtract 3/2 because I'm moving in the opposite direction. So that is pi over 2 minus 3/2. So 1 point for getting g of 2, 1 point for g of -2. Part B. In part B, let's change colors here. Find the value of the derivative, g prime at -3, and the second derivative at -3. Clean up my graph over here. Now remember earlier I talked about that connection point. Very important to make the connection that down here in your work, that g prime is f. So if I want g prime of -3, that's really saying what is f of -3? And when I come over here, 1, 2, and I look at -3, well, here we go again. We need this y value right here. So we're going to need to write the equation of a line. Don't be surprised in these piecewise functions, piecewise linears, that you have to write the equation of the line. So g prime of -3 is f of -3, which is 2. I don't think I wrote the equation of a line to get it. I guess you could do slope, rise, and run to get it as well. Yeah, that's what I said down here. You can write, I didn't write the equation of a line again, but you can write the equation of that line using the slope and one of the points. So you would find the slope, the rise, and the run here, and use one of these 2 points, and then substitute in -3 to get that y value of 2. And then the second derivative is really easy, because that's the second derivative of g is the first derivative of f, and the first derivative of f would be the slope of this segment, and you can rise, or in this case, rise and run to get the slope. So that's an easy second derivative value. First derivative, you have to do a little bit of work. 1 point for the first derivative, 1 point for the second derivative. Part C. I'm going to reset because it's getting messy. Find the x-coordinate of each point at which the graph of g original, has horizontal tangent. So that means that for horizontal tangent, we know that g prime is 0. Whoops. G prime of, come on, you can do it, x is equal to 0. For each of these points, determine whether g has a relative minimum, relative maximum, or neither a max nor a minimum. Justify your answers. All right, so we said g prime of x is f of x, so we're looking first for where is f of x equal to 0. Well, when we look at our graph over here, f of x is equal to 0 at here and here. So at x equal to -1, the first derivative changes from positive on this side to negative here, so we find a local maximum. At the second 0, the first derivative graph, which is this one, which is f, does not change sign, so we have neither a local max nor a local minimum. So in letter C, the graph has horizontal tangent line where there's that connection point again, g prime of x equal f of x equals 0 at -1 and 1. So first of all, had to tell us that what your thinking was. How did you figure this out? Second point is for reporting two values, -1 and 1. And the third point is for justifying correctly both of those values, that there's a relative maximum at -1 and nothing happening on G at 1 point for both correct. And then finally in letter D, for -4 to 3, find all values of x, which the graph of G, original, has points of inflection. Explain your reasoning. So we know from the All About Me sheet, I've said that in so many videos that I've been making, but most of the test is really, and even the C, was All About Me sheet. So G has point of inflection where G prime has local max and mins. Well, that's really the same thing then as saying G has point of inflection, because G prime, remember, as from our connection point, is F, has local max or mins. All right, so let's come up here. And so F, or G prime, has a local maximum at -2 because the graph changes from increase to decrease. At 0 because the graph of F changes from decrease to increase. And at x equal to 1 because the graph of F changes from increase to decrease. The graph of G has points of inflection, that's the ones we just talked about, because, and I would say F has local extrema at these values. Now they use the second derivative to justify, but the more appropriate justification here is to say that G prime of x equal F of x has local extrema, or change from increase to decrease or decrease to increase at these values. 1 point for the answer, 1 point for the explanation.